Hello and welcome again to my Physics Online video lecture series. Today's video is a continuation of the discussion of capacitors and capacitance. It basically extends our capacitors to consider objects that don't have just a uniform electric field. So this is a lecture that I guess is mostly peculiar to the calculus-based physics courses, meaning I don't really have a parallel lecture to this one for the algebra-based course. So let's get into it with that little preamble. I don't think that this is necessarily that complicated of a subject. It just happens to be one that works well if you're able to do integrals and doesn't work very well if you're not. In other words, an algebra-based version of this would kind of end up with almost like a just so story. Oh, the capacitance of this configuration is this, the capacitance of that configuration is that. So before we get into it, let's recall a couple things. The first thing is definition of capacitance. So capacitance is, or relates, if you'd like, stored charge to voltage drop. And oftentimes the stored charge causes the voltage drop or vice versa, but the capacitance just is defined as how much charge magnitude-wise is being stored on each of your conductors per unit voltage drop. Okay. The second thing to recall is that I kind of already said it, that the stored charge basically causes the voltage drop, and so that basically means that we expect delta V to be a function of Q, or maybe vice versa. So this kind of implies, let's say, delta V is some function of Q. Finally, the third item was the parallel plates capacitor, which had a uniform E field. And the result of the parallel plate calculation, we kind of had to determine that delta V was equal to E times distance between plates, and E in turn was basically charge divided by area times epsilon naught. And so what this ended up giving us was that the capacitance was epsilon naught times the plate area divided by the distance. So this was a nice example for that. It doesn't leave us with any idea of how to go about computing the expected capacitance, the geometric based capacitance, let's say, for a non-uniform field situation. And so essentially what we're wanting to do is determine what the capacitance is for a given configuration, which in turn would allow us to figure out if we have so much voltage drop, then how much charge is actually being stored. Okay, so how do we go about doing that? How do you go about determining the value of the capacitance for a generic system? Well, recall further, and this is from another of my introductory physics of calculus videos, that you can relate the voltage drop delta V to the electric field. So delta V can be related to the E field by, and the answer is basically delta V AB, so between points A and B, should look like the integral from A to B of E dot dl. Okay, and in turn, E might be determined from the charge present by using either Coulomb's law or Gauss's law, etc. So we have other principles that allow us to relate Q and E, and so now that we have those, we should be able to relate E and delta V. Now, in some sense, the process that we're using could just be taking this exact list that I've written out and reading it from the bottom going up. So we sort of like learn these things more or less in the order that I've stated them. But if you want to actually determine a capacitance, you take this list and reverse it, other than maybe this parallel plates portion. The entire rest of it, more or less, you start by figuring out what should the E field look like as a function of the charge. Then once you have that, you integrate it, E dot dl, to get your delta V. Now you have delta V as a function of charge, and now you can use C is equal to Q over delta V. So again, to state what it is that you're doing, you're reversing the review list. So first things first, figure out what E is as a function of Q. Second, determine V from E via integration. So third, you should now basically have the voltage as a function of charge. So you can get the capacitance by dividing the charge by that function. In other words, C is equal to Q divided by F of Q. So that is your basic process. What does it look like in actual practice? Right, so suppose you have a pair of concentric shells, spherical shells, as drawn in cross-section here. Inner one, radius R1, outer one, radius R2. We want to know what the capacitance is for this arrangement. So what we need to do is figure out if I was going to put some charge Q on these shells. So let's just draw a little arrow to a new diagram. I'm going to put a charge Q on one of the shells, and thus a charge of negative Q on the other shell. So this outer one could have a charge negative Q. By the way, we don't really care which shell has plus Q and which one has minus Q. I'm just drawing it this way for simplicity in some sense. So what would the electric field look like between these two capacitors? Well, as you know from E field lines, if these two are conductors, charges will tend to spread out uniformly on the pair of them. And so your electric field lines basically will just radiate outward like this. So this right here would represent E. And from Gauss's law, you know that E is going to equal basically 1 over 4 pi epsilon naught times Q divided by R squared R hat. And that is for basically R1 less than little r less than R2. It's 0 outside of that range. So this basically is our step 1. Step 0, I guess you could say, is draw a diagram. Sometimes that's a helpful 0th step. So we could go back over here and say 0 draw diagram. Always a good one. Alright, so here was step 0. Here was step 1. Step 2 basically says determine delta V from E by integration. So delta V from inner to outer, or from 1 to 2 if you'd like, this is a 1, 2, not a 12, should look like integral of E dot dl. And that integral, there is a minus sign. It kind of got absorbed into the equals sign over here, but there is a minus sign on that integral. So what do we got? We got an integral. This would be from R1 to R2. So integral from R1 to R2 of 1 over 4 pi epsilon naught q divided by little r squared, and our dl element could just be an r dr or dr r hat, I mean. So this is r hat dot dr r hat. And so my total integral, delta v12, if I pull all the constants out, so this is an epsilon naught, these guys basically all are constants and can kind of get pulled out. The r hat dotted with the r hat, this collectively is just 1. And so what I really have is an integral of 1 over r squared dr. And so that should be just negative 1 over r. The whole thing is negative, so that ends up giving me basically like a positive. And so my capacitance should be 1 over 4 pi epsilon naught times 1 over little r evaluated, q times 1 over r, evaluated from R1 to R2, bearing in mind that we don't especially care what direction we're going in, because we could choose to go from outer to inner, from inner to outer, so we just pick whatever makes this whole thing positive. So you can kind of like put an absolute value sign around the whole thing if you'd like. So what that ends up giving us when you evaluate is q over 4 pi epsilon naught times 1 over the smaller radius minus 1 over the larger radius. All right, step 3. So we've gone through steps 0, 1, and 2. Step 3 basically says C equals Q over function of Q. Okay, so that means that I have Q divided by 1 over 4 pi epsilon naught times 1 over R1 minus 1 over R2 times Q. And so that basically means that my capacitance for this system should be 4 pi epsilon naught divided by 1 over R1 minus 1 over R2. And if I wanted to turn that into a single sort of unified denominator, this ends up being 4 times pi times epsilon naught times R1 R2 divided by R2 minus, so for what it's worth, this right here is the total capacitance. I'm actually going to kind of leave it in this form though, because there's one other thing we could do, which is what would be the capacitance of a single sphere. In that case, R2 goes to infinity, so 1 over R2 goes to 1 over R2 goes to 0, R1 goes to. So that gives us the capacitance for a single conducting sphere. There are, of course, other common examples that you could try out for yourselves, some of which are worked out in textbooks, like what if instead of concentric spheres, what if you had concentric cylinders? You could even do other examples, like a more complicated example would be, what if you have 4 sets of concentric spheres with alternating charge on them, plus q minus q plus q minus q. What would be the capacitance of that arrangement? Basically, that calculation would look more or less the same as this calculation, but now you'd have a second integral, same function inside, but with a new set of limits. And so you'd have maybe a more complicated looking total capacitance, but the basic process is the same. So that's all that I was going to do in today's video to keep it a nice short video. So hopefully you've learned a bit from watching it. As always, thanks for watching.